Now let us discuss multigraph. We had promised in our introduction of graphs that we will come back to the idea of multigraphs. So what is a multigraph? Multigraph is again a pair of vertices and edges, but edges are not a set, but now they are multi-set. So for example, in this graph you will see 4 nodes and 7 edges. Now edges can repeat between 2 nodes. For example, A and C are connected by 2 edges. Notationally, you can see that E can be written as a multiset where same entry can repeat multiple times. Now we have a definition of multigraph. Now using this definition, we can define something called Eulerian tool, and the Eulerian tool can allow us to solve Königsberg's problem. So what is Eulerian tool? Eulerian tool is defined as follows. Given a graph or a multigraph, the tour is a path that traverses every edge exactly once and returns to the same node. Please note that this tour is not a cycle. Why this is not a cycle? Because a node can repeat itself. Edges are not allowed to repeat themselves. Consider this graph, several edges, and now let's walk over these edges such that you come back to the same node. Let's take the starting point to be C. So you go to A, then you go to D, then we go to B, then you go to A again, and come back from A, and then go to C. Now we are covering all the edges in the graph, and all edges are visited only once, and you come back to the same location where you started. Therefore, this is the Eulerian tour. Now let's look at the mathematical condition under which this tour must exist. And the statement is pretty astonishingly simple. Let's suppose you have a connected graph. The tour exists if and only if all vertices have even degrees. Now let's look at the proof. Again, we are given a graph which is maybe multigraph V comma E. We do induction over the number of edges in the graph. So let's consider the base case. There are 3 possible base cases. There are empty graph where there is no node and there are no edges, and naturally, since there are no edges, you can easily imagine a Eulerian tour, so that exists. If you have a single node and no edges, then again you have a existence of Eulerian tour. The third possibility we consider when you have 2 nodes and a single edge between them, then the tour does not exist because you can go from V1 to V2, but you don't know how to come back. So if your number of edges is less than 2, you can show that G has a tour if and only if all vertices of G have even degrees. Now let's continue and do the induction step. So what is the induction step? So we assume that you have a number of edges is more than equal to 2. Now if that is the case, since the graph is connected, there must be a node V2 such that V2 is connected to V1 and V2 is connected to V3. Such scenario must occur. Now we define G prime, a graph, as follows. If V1 equals to V3, then what we do? We remove these 2 edges, right? So if we are going from V1 to V2 and coming back to V1 again, then we remove these 2 edges and you obtain E prime. If they are different, we remove the 2 edges and bring in V1 comma V3. After this operation, what can happen is G prime can get disconnected. So we need to think about the connected components of the G prime, which we will call Gi prime. Now we will claim that if G has a Eulerian tour, then all of its connected components also have a Eulerian tour. And if all its connected components have Eulerian tour, then the original graph also have a Eulerian tour. This step of the proof, I will leave it as a homework exercise, but it can be easily seen. Then you can have tours from subgraphs and then can be stitched together in a way to obtain the tour of the larger graph. Similarly, you can take the tour of the larger graph and split into smaller tours such that you can get the tours of the smaller graphs. So please do this exercise at home. By induction hypothesis, we can assume that the theorem holds for Gi prime. Now let's look at another fact. Let's assume all vertices of G prime have even degrees. If that is the case, our transformation is such that it leads to all the vertices of G have even degrees. And it also holds reverse. Okay. Let's consider our transformation. Let's consider the first case of our transformation. When we are deleting V1, V2 and V2, V3 edges and adding nothing. Since there are two edges being removed at node V1, so then the degree of V1 reduces by 2, and similarly the degree of V2 is reduced by 2. Therefore, the evenness of all nodes remains the same. Similarly, you can check the condition when V1 is not equal to V3. The evenness of the degrees of all the nodes preserved due to this transformation. Now, because of these three equivalences, we can finally derive that G has an Eulerian tool if and only if all vertices of G have even degrees. Please work out the missing parts of the proof. It will give you great insight, understanding of the graph theory. Now we will look at another version of the graph, which is called a directed graph, and we will look at several definitions related to directed graph.